So we're going to continue working through our demonstrations here. I might try to see if we can get to the first lab exercise, if it looks like we're going to be moving at a good pace. But we'll see how many questions we get in and stuff like that. And definitely want to prioritize questions over labs because we only have this short time together, but we may have a chance possibly to let you work on the lab a little bit here in class. All right, so let's take a look at the, let's see, we're looking at the input enhance. Yeah, so here's our def num, and let me come down to here. And let's see. Okay. So here's what's different about the input enhanced versus the earlier version we were looking at. I've incorporated a while loop so that if you type in an invalid input, it'll ask you to type it in again, right? So at the bottom of the except here, we've handled the error. Now it loops back up. So if I were to come into here and run this, and I typed in, let's say, the letter R, obviously that fails. I can type in 2. If I type in the letter Y, type in 3, I get the result. What would that look like using the earlier code that we had for doing the match? What would it look like to try to put that into Rust? So first of all, Rust supports an infinite loop mechanism. In Python, we use the idiom while true because Python doesn't really support just an infinite loop out of the box. You have to make one. And while true is typically how you see it done. In Rust, there's actually a loop called loop. And loop runs infinitely. In order to exit out of that loop, you have to use control flow statements like break and continue, okay? In this code here, we have the loop wrapping our variable and our prompting and our flushing and our redlining. We have our match statement in here with our OK and our error. If the user types in invalid input, then it will do a continue and go back to the top of the loop and have the user type in the number again. If the user types in something that can be parsed, then it will use the break statement, which breaks out of the loop, and num will be the return value that comes back from the function. So the break breaks out of the loop. The num is the return value to then exit the function. Now let's take a look at this code right here. This is what's called a turbofish. Now, looking at the syntax, you can probably kind of guess why it's called a turbofish, right? We kind of have like the head of a fish here, and then we've got these colons behind it. I'm not sure if that's supposed to represent like, water being pushed back, or maybe it represents the back end of the fish. But it kind of gives the impression that our fish is moving fast. At least that's my understanding of what turbofish means. I haven't spent a lot of time researching the origin of the word or what are its, underlying meanings and stuff. But whenever I've thought of turbofish, that's kind of how I look at it. So what's happening here on the parse? What's interesting is that in our earlier code, where we made use of the parse, right? Over here, for example, well, not the Python example, the Rust example. Earlier, when we made use of the parse, I didn't have to specify a data type. Over here, I am specifying a data type. The question is why? Well, one of the things that that Rust is very good at doing is inferring the static type of things based upon the code surrounding it. For example, you'll see that when I declare this variable input and set it equal to a string, I don't have to declare the actual variable type on the variable itself. It can infer from the assignment of that first expression what the data type of input is going to be. Well, down here where we have our num input, the return type is i32. You'll notice that here I have my trim.parse, and it knows to parse it to an i32 because of the return type there. Over here, it's not quite so clear what that type is going to be, or if you want the type to be something else, how could you explicitly put that? And that's why I've got the turbofish there. We're going to tell it to convert it to an i32. Now, for fun here real quick, let's actually take out the turbofish. And let's see if Rust is smart enough to do the conversion automatically. So if you take a look at the code here, you can kind of follow the num, which is the return value, comes from the OK. The OK comes from the result, which comes from the parse. There is enough information there. It might be able to determine what that type is. Let's run this code and let's see if this is going to work. Okay. So we actually have the type returning there as an i32. So if we come down into here, we'll run this, enter the first number. Hey, look at that. It was smart enough to figure it out. What if I were to change this instead to be an F64? Let's examine whether or not the parse is doing an i32 by default, or if it's really inferring the F64 from the return type. These are the kinds of things that I have found to be very helpful when learning a programming language. Make little tweaks like this to your code and see what it does as a way of developing your understanding of how this stuff is working. So if I do that, this code here should still work. And I should be able to get my result back. So let's run this code. And we'll say 1.2, 3.4, and I get 4.6. Look at that. So it was able to infer without me putting the turbofish there. In this case, it works out okay. Not always, number one. Number two, you can always put the turbofish there just to make sure it's doing what you think it should be doing. You'll also notice here, we've got our code linter and the compiler complaining. One of the things you'll find with the Rust compiler is it's very, very good at picking up compiler errors for things. Like, it's really good. In fact, when the compilation fails, a lot of times it gives really helpful error messages. So for example, if I were to come into here and go into demos, Rust, and I believe we are in the 5th demo, and I say cargo build, so just kind of see where we are. We're in the folder that has the cargo lock, the cargo toml, and the source. If I come into here and say cargo build will just build the software. Cargo run will execute it. Take a look here. Break num, expected F64, found in 32. You can convert an int32 to an F64, producing the floating point representation through using the into function. In fact, for fun here, let's see if we can actually do that. You will love the Rust compiler when it comes to these little help messages. It's probably the most helpful compiler I've ever worked with in terms of helping you through bugs, trying to learn more about the language and fix things that might be wrong. So if I come into here, let's highlight this code. I'm going to do Control-I, and I'm going to type in fix. Let's see what Copilot suggests to me in terms of trying to fix it. So Copilot is going to suggest that I use the into function. With Copilot, when you use the in editor chat mechanism, always click the little plus sign to see what's going to be removed and what's going to be added. Sometimes in VS Code, the inline Copilot mechanism will delete more code than you want, and that can be really frustrating. So double check what's going to be deleted and added, and if it looks good, go ahead and click accept. All right, so what does into do? Into does this conversion. Well, how does into know what to convert it into? Once again, based on the return type. Okay. So right there, we were able to use the compiler. Well, first of all, we were able to modify the code and kind of explore how things were working. Number two, we found a way to break the code. The compiler gave us a great error message. We were also able to use Copilot that also gave us basically the same solution. And then it was able to fix the code for us. I cannot stress this enough when working with Rust. When you're first building things, you're going to make lots of mistakes. You might have made a lot of mistakes in Python, but you're going to make a lot more mistakes when it comes to Rust, just because of all of the other requirements that it puts on you, especially as it relates to memory safety. Using a tool like the compiler and its error messages, or using Copilot to help you fix those bugs, is going to be key. Okay. So anyways, there's our fix there for the code. Now, what if I change this back and we just did the F64? What if I type in an integer without a decimal value coming after it? So I type in 2. There you go. Okay. So it was still able to work with integer values. I didn't have to type in an actual dot. Sometimes I find with Python and its type hints, it can be a bit strict between like ints and floats when you're putting literal values and stuff into the code. And so one of the things I always check in languages is, how friendly is it for working with integers relative to an expected floating point value. Okay, cool. Let me check the questions here and see if we have any. The Turbofish is more like a generic. So in fact, we're going to take a look at generics in this class. We're going to take a look at writing your own generic function, things like that. And so it's definitely more like a generic is the way to look at it. That type hint is actually telling it what type to convert it to. Whereas the type hint in Python is just telling you what type it is or is expected to be. But it doesn't actually, it isn't used beyond just doing that analysis. Okay, let's come back over to here and let's take a look at our next example. And before we look at the Rust version, let's come back over to the Python version first. Okay, so we've looked at some basic constructs here, creating variables, defining functions, calling functions, a little bit of pattern matching and enums and some error handling. Let's start getting a little bit more into building something real. Whenever you go to build that first real program with a language, generally speaking, the first thing that you ask about is, how do I define a class? How do I define a struct? If you're doing Pascal programming, how do I define a record? How do I create something that models the real world, which generally means having a number of data attributes combined together into some type of container? Okay. Now, class color run is the approach that we use in Python to take a bunch of data attributes and combine them together into a container. Sure, there's a few other ways. You could use things like dictionaries and stuff like that. But if you're trying to build a proper program and you want to have really good type definitions, really good code completion, you're going to go with a class like color here. Even if that class doesn't have any methods on it, you're still going to use it like you would use a struct in C or C++, where you just are combining a bunch of attributes together, putting them in a container here called color. In this code, I have a method here called print color. Please notice print color is not a member of the color class. We will eventually have code where that is the case. But for right now, I just wanted to demonstrate calling print color as an independent function. So here we have our type int for our color. We can pass a color into print color. It prints it out on the screen. If I want to create a new instance of a color, I simply call color with the parentheses, pass in the parameters related to the dunder init, and then create my color, and then I can print it out. So if I came into here and I ran this code, you would see there's the color printed out just like that. No big deal. Now, in Python, not Python, in Rust, we have structs instead of classes. Now, Python is a classical object-oriented programming language. Literally everything in Python is an object. Everything from primitive values like an int or a float. Functions are objects. The class definition itself is an object. You use the class object to create instance objects. Everything in Python is an object, okay? All of these objects in Python are stored in the heap. Now, if you actually study the internals of Python, you learn about arenas and stuff like that and how the actual Python memory is really laid out. I'm just going to use the term heap to represent dynamically allocated memory at runtime. I'm not going to get into all the little details of how Python memory is organized. It's an interesting thing to know about, but not really critical to just doing everyday Python programming. But in Python, because it is a dynamically typed language and everything is an object, all of these things, for the most part, there's a few little exceptions with like numbers, I think, between -5 and 101 or -1 to 105, whatever. There's a few little exceptions, but basically everything in Python is going to be some heap allocated object. Rust is different. First of all, we don't have classes, we have structs. Structs only hold data. Can I associate methods with a struct? The answer is yes, but we'll talk about that later. But right now, apples to apples comparison. This class just has data attributes. This struct just has data attributes, okay? The struct has a name, just like class color. We can use that name down here to create the instance. Kind of looks a little bit like object initializers in C#, or if you were doing like an object literal in JavaScript, is kind of how that looks. Python has that more constructor-like approach like you would see in C++ or in other kinds of C# code or Java. Anyways, this struct that I'm creating an instance of, this struct is not heap allocated. Now, we could heap allocate it using things like box, and you'll see that in the very last demo in the class. But when we're creating all of these variables here, for the most part, they're not heap allocated. Probably the one exception that you've seen so far is like working with the string, because the string grows and changes in size. But Rust out of the box, when it works with something like this struct here, this struct has a fixed size at compile time, and it is on the stack. It is not in the heap. So up here, when you create your color, you're working with dynamically allocated memory in the heap for storing the color object. Here, we're creating this color struct that is statically allocated on the stack. If you've never studied the heap versus the stack, maybe you came to Python from another discipline, and Python's just a tool that you use to do your scientific work or other things, and you've never studied how memory works in computers, it'd be worth your time to go learn more about the heap and the stack and all of that if you're going to get into Rust programming. Things like the heap and the stack also factor into like C++ and C and things like that. When you work with languages like Java, C#, Python, JavaScript, that heap stack distinction is kind of hidden from you because the way the memory is managed for you. But in languages where you're having to really think about memory, the heap versus the stack is a big deal. Anyways, this color one is going to have properties on it like .name, .hexcode, so on and so forth. Just like you would access them over here, you access them the same way over here using the dot notation. Now, the question is, what do we call this thing? I can call it the color struct, but is that referring to the one that I'm creating in memory? Or is that referring to the definition up here? In Rust, I will refer to this as the color object. I don't mean an object in the sense of like classical object-oriented programming. By object, I just mean some piece of memory that has these different data attributes collected together. Okay? All right. These different data attributes collected together. You could call them a struct instance if you wanted to, I suppose. I just call them objects. One of the things that you'll see like in the C programming language, which doesn't have classes either, it just has structs. People refer to structs as objects in C. So if you talk to a C programmer, they'll refer to the struct instance as an object, but they don't mean classical object-oriented programming. In JavaScript, we call objects objects, even though JavaScript is not a classically object-oriented programming language. So as we go through and talk about instances of structs, I'll probably refer to them as an object. Just be aware that I'm not talking about Python objects or C++ objects. I'm just talking about objects in the sense of you might call an instance of a C struct to be an object. Okay. Anyways, with that taken care of, let's continue on our discussion. Now, this is where you're going to kind of have your mind blown away with the implications of memory safe programming. If you've never done Rust before, you've probably never thought about the thing that I'm going to mention next. And when you start to think about it, you're going to see why this is something we could think about. And you're going to see why this becomes an issue in Rust because everything is so memory safe. Before I make any changes here, I'm going to run this real quick so you can actually see the output that it actually works. Okay. So both programs currently work as is. I'm now going to make a change to the Python program. All I'm going to do is say print color, color1 again. If I write my code like that and I hit the little play, what do you see? It outputs color red twice. Pretty amazing, right? Yeah, not so much. What happens in Rust if I do that? What if I take this statement here and I call it twice? This, for me, is really the first example that a developer comes across where they're first using Rust. They're like, oh, this is really cool. I'm a Rust programmer now. They go to do something like this, which should obviously work, right? Yes, there's a red squiggle, but let's run this and let's see what actually happens when it runs. It doesn't even compile. Okay, think about that for a moment. It doesn't even compile. We're not talking about we did something and it breaks at runtime or whatever with code that looks perfectly fine. We just didn't understand. It doesn't even compile. And here's why. Let's look at the Python code here. When I called print color on line 14 and it called the function on line 7, and I passed to the print color this color1 object, who owns the color1 object once I pass it? Does the main function still own the object? Does print color now own the object? See, here's the thing. In programming with pretty much any other programming language, if a piece of code has a reference to something on the heap, it can change it however it wants to. How do we access things in memory in a program? We do it through a variable. What does Rust do? Rust uses these variables to track who has access to what in memory. When you take this variable and pass it as an argument into the function in Python, you're just passing a reference through, and anybody can take that reference, access the object, and change the value. No big deal. I run that, I get hacked. And literally, all of us have programmed with this kind of approach our entire programming careers. So we think this is just the way it should be done because every language allows this. Every language behaves this way. And this is where a lot of the things like bugs related to memory become an issue in large pieces of software. So, and it's not really the by ref or by copy. The issue is I passed the reference, so anything that has the reference can modify it. But is that really what I should be doing? Let me ask you this question. How many people here have ever done any React programming in JavaScript? Like you built a web page with React at some point, by show of hands. Anybody? Okay. For those of you who have done some React programming, what's one of the fundamental principles in React? If you were to write some React code, right? And you had some component logic here. And let's say you passed in props. For those of you with React experience, am I allowed to take props here and say props.items and give it a new value? Is this allowed in React? Yes or no? In the chat real quick, those of you who have done some React programming. Is that allowed in React? Am I allowed to change the props object being passed in? Yes or no? I'll give you like 15 seconds, then I'll give out the answer. Okay. The answer is no. You are not allowed to do this in React. In fact, this is the single worst line of code a person could put in a React component. Okay? This is absolutely not allowed. The question is why? Well, the thing that calls item list, right? So let's say I've got my items here. The thing that calls item list owns the items. It owns the items. Yes, item list is allowed to read the list of items and print it out. But if item list were to access this object in memory and mutate it, it would be changing data that belongs to something else. Now, can JavaScript prevent this from happening? No. No other language can prevent this from happening except for Rust. Because with Rust, you have to define the relationship between the variables outside the function and the variable's data that's passed into the function. You just can't simply pass a reference and start changing it. Okay? All right. You have to define what that relationship is. Now, over here in Python and literally every other language, if you pass that reference, there's nothing to protect you from changing that object that was passed in when it shouldn't be changed. In Rust, however, there is. In Rust, what happens is we are moving the color one struct ownership to the print color function. And let me drag that over. We are moving the ownership. So here's what happens. Once I move the ownership, guess what I can no longer use? I can't even come in here and reference the struct anymore. I can't pass it into something else. I can't use it anymore. It's kind of like if you have a car and your friend needs a car. You take your car and you give it to your friend because you're a kind person. Can you drive your car anymore if your friend has it? No, you can't. You've moved ownership of the car to your friend. You no longer have a car. That's what happens here. We're moving ownership of this struct into print color, which means it's no longer available here. By a show of hands, how many people think you could find this to be really frustrating? You're trying to build a program, you're getting excited about Rust, you call a function, and now all of a sudden everything breaks and you're like, what am I going to do? How am I going to fix this? This is where people first realize Rust is really different from all the other languages they've ever used. This is what we mean with memory safety. We're not just arbitrarily passing references around and people can use them or change them or whatever. We have to be super clear about the relationship. So how do we fix this? Well, obviously, calling the function that way is not really going to work. What we're going to do is this. On the function here, we're going to modify the parameter to basically say that we're passing a reference in. Now, you're like thinking to yourselves, well, Eric, we passed a reference up here. Yeah, but not the kind of reference you're thinking of. This is basically going to be a borrowed, read-only, immutable reference. So for example, if I try to come into here and say color dot name equal to string blue, it's not going to let me do that because color is coming in through an immutable reference, not a mutable one. So if I try to modify this data, it won't let me because ownership is not being transferred to the function. Ownership is not being transferred. So I can't do this. And I'll show you how to transfer ownership in a moment. Or not, I'm sorry, I'll show you how to make it mutable in a moment. But ownership's not being transferred here. Instead, what's happening is we're passing a read-only reference. Remember, all variables are automatically immutable in Rust. So if you want to be able to mutate them, you have to be explicit. So not only is this immutable in here, but we didn't mark this as mutable, so it's not going to be changeable anyways. But the point is, this is coming in as a read-only reference that's borrowed. So now that I've marked that as borrowed, when I call the function itself, I explicitly put my ampersand there saying I'm passing in that immutable reference, that read-only reference. Now watch what happens when I run the code. It works perfectly fine. And this makes sense if you think about it. Because I know this is going to be an immutable reference going in, I know that that other function is not doing the things that an owner would do. An owner of a car can get the car repainted. The renter of the car cannot. So this function is renting the variable and it can use the value, but it can't change it. Because main still owns the value, it can now use it again and pass it into something else if it wants to. Okay? This is one of the big ideas in Rust that people initially stumble over, asking themselves which block of code actually owns the memory. If it owns the memory, it can make changes to it. If it doesn't own the memory, it can only read it. And Rust enforces this at compile time. Okay? All right? So that's the big idea, or one of the big ideas, as it relates to working with memory in Rust. Now, what if I wanted to have the ability to actually change color one? First of all, I'd have to mark this as mutable. Now check out the Rust compiler. It comes back and tells us that we can remove the mute keyword because we never attempt to change it. The Rust compiler and Clippy, which is one of the code analysis tools, is very aggressive about not having unused variables, about not applying keywords that shouldn't be applied because that behavior is not being used. In this case, adding this mute is going to cause us a problem unless we actually go to mutate it. Now, if I come into here and say color1.name, and we say green, now you'll notice the yellow squiggle here went away. Why? Because I'm actually mutating the value. Will this code here still work? Can I take this mutable color struct and pass that immutable reference into the function? Well, if we hit run here, we'll see it works perfectly fine. Now, what if I wanted to modify this inside of this function? How would I make that happen? I'd have to pass in a mutable reference. I'd have to tell it explicitly that mutations are allowed. So now I can modify that. My problem, though, is how do I pass in a mutable reference here? Is that even possible? Can I pass in a mutable reference and still retain ownership? Let's see if this code will run. There we go. So now what I've done is I've told Rust that I'm passing in a mutable reference. It's going to borrow that mutable reference. It will be allowed to make modifications to that variable. And then, of course, I still own it inside of the main method. Now, before we continue on, just for fun real quick, let's say I come into here and have print color 2. And what I'm going to do is I'm going to remove the assignment of blue. If I assign blue here, is it really changing the memory from out here? And will I see that change reflected when I call print color 2? Let's run that. And there you go. It really actually is borrowing a mutable reference, and it's going in and actually modifying that name property on color. Okay. So this would be, for example, like giving your friend the car for the weekend. And as part of your friend taking the car for the weekend, you ask them to go get to go get new tires on the car for you. Right. Or you ask them to paint the car for you. Right. So they can use it, but they have permission from you to make changes to the car. And then they bring the car back to you at the end of the weekend. Okay. Let me pause here for a second. And I'm going to take a look at some of the questions we have kind of showing up here in the chat. And then we'll continue on. Right. So yeah, so ownership here has to do with whoever owns the memory is allowed to change it. You by default, when you pass something in, ownership is transferred. And if you think about it, that's actually a pretty good default as to why. Because that's how most people are going to write their code, and it's going to trigger the compile error. So if you try to access that later, it's going to give you that compile error and force you to then think about passing a reference or an immutable reference or a mutable reference, and then updating your code accordingly. And let's see here. Okay, so here's the interesting thing. This mute applies to everything that you access off of that struct. This is not like JavaScript where like the variable's immutable, but the object on the heap is not. So if anybody's ever done JavaScript before, you can have an immutable variable, but the object on the heap is mutable. So you make the variable as const, but then you see people changing the object on the heap. In Rust, it doesn't really matter where the object is stored. If the variable is immutable, you cannot change anything through the variable. In a sense, Rust kind of behaves the way that a new JavaScript developer expects JavaScript to behave, but JavaScript doesn't really behave that way. Hopefully that helps answer that question. Okay. All right. So there's going to be a lot of mutes and references and stuff like that all throughout your code. That's how Rust achieves that memory safety at compile time and avoids the garbage collector, but also avoids the manual memory management nightmare of working with C or C++. Okay, cool. Let me go ahead and close that and that. And let's come on over to adding some methods here. So probably the next question I would have if I was going to build a real program was, okay, I've got my data structured. What about putting some methods with that? So as you know, starting really in about the 80s, that was where the idea of having this concept of a class, which combined data attributes and behavior into the same kind of structure. Things like, I believe, Smalltalk was one of the first ones, and then C++ became popular. Python came out a little bit later in the early 90s, along with Java. And the world that we program in today, whether you're JavaScript, Python, C#, Java, whatever, the big languages that lots of companies use, most of us are used to working in this kind of class kind of environment and combining the data and the functions together within the same syntax structure. So here I have class color, same dunder init as before, but now what I've done is I've promoted the print function to be an actual member of the class. I've also added a static method to the class. So a static method is one that is available on the class object itself. This kind of method is an instance method that gets bound to a particular instance. The reason I have the static method is not because you would actually use one in Python for this purpose, really, but I have the static method here to help relate to the Rust code that you're going to see here in a moment. Anyways, you'll see here on line 20, I referenced the static method new off of the class object. Into new, I pass the two values, red and the hex code. I take the created object, assign it to color1, and then I call the print method on that object. In Python, if you want to reference the instance inside of the method here, you use the self keyword, or the self is going to be the first parameter. It's not really a keyword, but the self parameter will be the first parameter of the method, and I can access the attributes here on this particular instance. Now, what would this code look like in Rust? So we'll come over here to Rust. You'll see here at the top, I have the same struct as I did before, but you'll notice there's no methods defined as part of the struct. The struct, the collection of data, is this independent entity. Another language that makes use of this approach would be Go. If anybody here has done any Go programming. I've done a little bit of Go programming over the years, not really any recently. But if you go on YouTube and stuff and look up Rust, you'll see a lot of people comparing Go to Rust. And that's because there are some similar concepts in terms of things like structs and the way functions are defined for those structs, things like that. The big difference, though, between Go and Rust is that Go is garbage collected. So when people are looking for something that I guess kind of feels a little more like Rust in terms of these structs, but they want garbage collection, they go over to Golang. Okay, now, how am I going to connect methods to color? Well, I'm going to do that by creating this implementation block or impl block called color. And I'm going to put two methods on here. Now, in Rust, there is no concept of a constructor. So in a language like Python, dunder init would be our constructor. Rust does not have a constructor type of syntax. Rust is not a classical object-oriented language. Sure, there are, we can use some of the object-oriented patterns and stuff in Rust, and I'll show you one of those later. But strictly speaking, from a language perspective, Rust is not a classically object-oriented language. So a common convention in Rust is if you want to have a function execute to create an instance of your struct, you can do that by creating some type of new method. It can be called anything you want it to be called. But in this case, following the example of the string, I'm going to say new and create a method here where I have my name and I have my hex code. And then I'm going to return back my actual color struct here. As part of the impl, I also have my print function. You'll notice, though, the big difference between them. In the new function, there's no self parameter. In the print function, there is a self parameter. The self parameter is what tells Rust this is going to be an instance method versus what you might think of as a static method. Now, Rust has a special term for static methods. They are called associated functions. For instance methods, they are called method functions. Okay, method functions. What's interesting about this method function? Notice the ampersand self. What does that mean? That means if I try to type self.name and give it a new name, guess what? I get an error because ampersand self is an immutable reference. So even in its own method function, its own instance method, it can't modify the underlying data on the struct because it's an immutable reference. By a show of hands, who feels like this could get really difficult to work with? Like you're having to think about a couple of extra things that you don't really consider in other programming languages. Every time you want to try to reference a parameter or struct in memory or whatever, right? Yeah. It's definitely like that in Rust. Now, initially, you will lose a lot of time. Don't get me wrong. The Rust compiler does a great job with error messages. Copilot does a great job helping you. But because you have to think about this extra dimension all throughout your code base, it will slow you down initially when learning Rust. However, it's like anything else. Once you get used to thinking this way, it's not that big of a deal at all. And in fact, what it will cause you to do is come back over to your Python code and look at your Python code through a new lens and recognize some possible problems in your Python code. Not that Python really has the ability to do things like this at this level, but it will help you identify areas where your Python code could have runtime bugs and other issues because of how that memory is, in fact, actually being managed and used in the application. Anyways, there's our print method there, okay? And then here we have our new. Right, so what happens is any method defined inside the impl block will either become a method of the struct itself or a method of an instance of the struct. Okay? All right, so let without mute is the same idea as const, except that it applies to everything the variable points to. Okay? Unlike in JavaScript where it just applies to the variable itself. Let without mute, everything's constant. It cannot be changed. Let with mute, you can change it, but only if you have ownership, or you can borrow ownership. Okay? Now, down here, I create my color new. This is why I made the code look like this in Python. So you could see that this new is similar to the static method, except it's called an associated function in Rust. and then we call color1 print, and it's a method function in Rust. So if I come into here and run this code, there's the output that we had before. Now, there's something else new in here that we really haven't talked about yet. We're going to talk about it now. At string, or I'm sorry, ampersand string versus the, and let me just grab it from here, versus string new. This is a string slice. Number one, it is immutable. It is read-only. Number two, it represents some sequence of characters in memory. There might be an underlying actual string object that you've created underlying that slice, okay? But that slice is like a read-only view into that string object. So what that means here is I can access that slice of data and utilize it in a read-only kind of way here. Now, here's the problem. These are actually of type string. This slice belongs to a different string variable. It belongs to a different string variable. I can't come in here and assign it, because that would be taking that block of memory and assigning a reference to that block of memory to another property that can't access it, can't change it. So what we have to do is we have to take this slice and use the value in memory of the slice to create a new string object that will then belong to the color struct. So we're taking another string's slice, a slice of some other string's memory, using the value stored there to construct a new string object and assign that to the struct that we're creating here. Okay. In a sense, we're basically copying the data over into a new object in memory. So now I have my name and hex code created from the slice. So down here, we passed in these string slices, converted them to actual string objects to create the color. Okay. Now, can I come into here and say color1.name equal to that? Can't do that. Why? Because color1 isn't mutable. Okay. Can I do this? Can I push another character onto the string? And the answer is no, I can't. Why? Because the string is not mutable. Do you see this right here? This is like what's so different than every other language. Every other languages might prevent you from doing something like this, right? They might prevent you from assigning to the variable itself. Other languages might prevent you from doing that. But can you think of any other languages that when you reach out to something on the heap, that it somehow knows that that method is going to somehow mutate the underlying piece of data? Well, the question is, how does it know that? I'll tell you how it knows. Because somewhere there is an impl for string. And in the impl for string, it has the at mute or the ampersand mute applied to the self. And that tells Rust that inside of this code, we're going to be doing a mutation. So when you take color1.name push, it knows you're going to have a mutable reference. So it's able to discern by calling push just as easily as it can here. It can discern that you're trying to mutate color1.name. Everybody see how that works by a show of hands? Because you apply that mute as part of the variable declaration, it knows which methods have the mutable reference. And so it knows when you're going to try to change something at compile time. And this is so different than any other language. Sure. In some languages, you can mark an attribute or a property read-only, and then you can't change it. But if that attribute or property points to something on the heap, there's nothing on the heap that prevents you from changing stuff or it even knowing that you're going to change stuff. But it's because of these ampersand and ampersand mutes that we apply, specifying immutable and mutable references, and having that default behavior of move. That's what tells Rust what's actually happening to these variables in memory, whether we're just reading or making changes. And that's one of the big ways in which Rust is achieving memory safety. Okay, that's how it's achieving memory safety. All right, let me take a look here at the quick questions. Yeah, there's no real special treatment to strings. There's just a sequence of characters. Let's see. So if a function doesn't have ownership of a variable or borrow ownership using, does that mean the function not only cannot write to that memory, it also cannot access it for reading? Well, here's the thing. If you pass the variable into the function with nothing, with no ampersand, then it does a move. If you pass it with an ampersand, it's an immutable read. If you pass it with ampersand mute, you can mutate it. So there's no way that you could call that function in such a way that one of those three operations doesn't occur. Putting nothing on the actual variable is going to do the move by default. So the other ways give you more fine-grained control over that relationship. Okay. Hopefully that helps answer the question. Okay. Now, super cool stuff here. I am not aware of any other language that has this level of control over how memory is utilized. There might be one, I'm just not familiar with it. There are other languages that try to do a good job of cleaning up allocated memory, not just garbage collection, but for example, the Zig programming language. It's kind of a drop-in replacement for C. It gives you manual control over the memory, but it gives you a couple of language keywords like defer that will free up the memory once a function ends or something like that automatically. But in terms of having this level of control, Rust is really the only language I'm familiar with that does this. If anybody's familiar with a different language, feel free to share with the group. Okay. All right. Right. So once it receives so the thing is this. It's the difference between move and borrow. If you just pass that variable into the function, it's a move, not a borrow. So move means you're transferring ownership. When you use the ampersand with or without the mute, it's a borrow. So no ampersand is a move. With the ampersand is a borrow, if that helps. Okay. All right. And move means giving up ownership. Borrow means giving it temporary ownership. Okay. All right. So now we get to the point where our application is starting to grow in size, right? And we need the ability to spread this over multiple files. Some languages make it really easy to do multiple files. Think, for example, C# and Java. If you use Visual Studio, IntelliJ, whatever, you want to add a new class file to your project, you add it and everything just magically works, right? Other languages can be a little bit more tricky. In the JavaScript world, dealing with all the module systems and figuring out how to import things can be a little bit difficult. Even in Python, a little bit, depending upon how you run your code, running it as a module or just an independent script, doing relative imports versus absolute imports. Even in Python, pulling in modules can be a little bit difficult when you're first learning how to do it. Well, how does this actually work here? Like, how is this module system in Python working? Essentially, in Python, every file is a module, and every module is a file. When you import color, it actually runs this code, produces a module object in memory, and then you're basically referencing properties on that module object, like the color attribute, which refers to the color class. Okay. But this is actually an object, a module object loaded in memory. It's a singleton. So if you import the same module multiple times, it only gets loaded once. That module object in memory is something that you reference here using the whole dynamic typing heap memory management system. And then you reference that color class object just like we referenced it in our earlier code. No big deal. What would it look like to do the same thing here in Rust? So in Rust, over here, we're going to create a new Rust file, color.rs, no big deal. We're going to declare this module here over in the main file. Now, this isn't a use statement. This is just declaring the color module as part of our program, okay? So here, color.rs is a module, okay? We're going to take all that color code, the struct and the impl color, and we'll move that over here to the module. Now, once I move this to the module, all of this code can only locally be used in the module. If I want the struct, the various methods on impl color to be utilized in another file, I have to mark them with pub. Now, I don't want you to overthink this. This is not like classical object-oriented programming where you've got, private, protected, public, and stuff like that. In Rust, by default, everything is private. If you want everything in a module is private. If you want to expose something from one module into another, you mark it with pub. In Python, its module system is like the opposite. In Python, everything in the module is public. if you utilize a language like JavaScript, JavaScript is kind of similar to Rust in that everything is private unless you export it, which would then make it public. Python, we're all used to everything being public. In Rust, everything's private unless you mark it as public. On the struct color there, I marked the struct as public, but for the impl color, I marked the individual methods as public. Okay. So it's possible you could have methods in here that should remain private, not usable over here. And you could have those private methods. And then over here, you can only make use of the public ones. So same basic code as before. You will notice I have my use statement here. And this use statement is actually missing one important thing. This should actually be use crate. And that's really the correct way to reference it. In older versions of Rust, you could put color, : color, and that was fine. But the correct way in Rust to reference modules in your use statement, to reference modules that you've created as part of your program, is to put the word crate in front of it. It's kind of like doing the importing of modules using an absolute path in Python as opposed to a relative one. So we'll say crate, and then it will pull in our color there. Now, unlike Python, where this module is loaded up as a module object in memory, in Rust, all of this code is compiled together to make one big binary. So this source code is not like loading up a module object or something like that. It's taking our usage of all of this, running it through Rust's amazing static analyzer, not just doing all of the memory stuff, but all of the other optimizations that are performed, and then producing for us a single binary. Whereas in a Python program, you would distribute individual Python files that all get loaded off the disk at runtime, even in the final application. But here, we are compiling all this together in a binary. So Rust modules are similar to Python in that a file is a module. We can import. We typically import using that absolute path. But they're different in that Rust modules default to private, and you have to make elements public that you want to use in another file. And it's not loading some module object in memory at runtime. This is all being compiled down into a compiled application. Okay, so there's our discussion on modules. All right, we are coming up on our lunch break here. Let me ask this quick question before we take our break here for lunch. How many people, by show of hands, are surprised at how Rust actually works? Is there anybody who came in here thinking it was going to be one thing, and now you're seeing the code and you're like, wow, this is really different than what I expected, by show of hands? Okay, good. Always fun to learn new things, different things. So before I let you go, I'm going to two quick things. Number one, keep in mind that that the reason we want to use Rust, like remember I told you when we do something hard, if we don't remember why we're doing it, we tend to, try to avoid it or something like that, or do something else. The reason we're doing this is we want memory safe applications. So if you've ever built something that had exploits related to memory issues, you could see where this would be really helpful in helping you better understand that. Also, too, because it is compiled, Rust applications are almost as fast as C applications. So definitely 1,000,000 times faster than Python. Not quite as fast as C. You can still write a faster C program, but it really is amazing what you can do with this.